Hello again. Today's lesson is on ratios and rates. Ratios and rates are very common and very useful. They help us scale things up and scale things down, and they also tell us how one thing compares to another, not in terms of being heavier than or lighter than or taller than, but in terms of being maybe twice as large or half as big. So let's begin. You've got your guided student notes ready. I'm going to scroll up and we'll start. Oops, that was a little far. There we go. We'll start with the ratio. A ratio uses division to compare two quantities. And the quantities that we're comparing need to have the same units. You can see a ratio many different ways. We can write it just like this. We can compare quantity A to quantity B. Or you can express a ratio with a colon, and we can see A colon B. Or you can express a ratio as a fraction, and we have A divided by B. With a fraction, you can clearly see that the division is happening. Let's try an example here. Maybe that will be a little easier. We have some R502 refrigerant. In order to make this, we have to mix R22 refrigerant with R115 refrigerant. It takes 61 grams of R22 combined with 64 grams of R115. So we'd like to write the ratio of R115 refrigerant to R22 refrigerant. And we can do this three different ways. The first thing we have to figure out is what number comes first. Right now, the ratio says R115 refrigerant compared to R22 refrigerant. So the R115 acts as the A, and the R22 acts as the B. Well, let's see, how much of this R115 do we have? That would be 64 grams. So that's our A. And the 61 grams, that's R22 refrigerant, that's acting as B. So we can say that the ratio is 64 to 61. Or we can write 64 colon 61. Both of them mean the same thing. We can also write this as a fraction. And the fraction is kind of nice for today, because then I can put in the units, because we have 64 grams of R115 compared to 61 grams of R22. And I know, you're going to ask, how come we didn't use the units when we wrote the ratio before? And we didn't use them because they cancel out. And we can see this in the fraction. Grams in the numerator cancel with grams in the denominator. What we really have is 64 compared to 61. So that's something that we should write down. I'm going to change color over here. Let's see. Common units. Cancel. Just like common factors. And this is why ratios have no units. And that's really a nice thing, especially when it comes to interpreting a ratio. So what does this mean? It doesn't mean that we always need exactly 64 grams of R115 and exactly 61 grams of R22. What it means is that for every (64 grams) of R115, there are 61 grams of R22. So we could double the amount of R15, and we would also need to double the amount of R22. We could take 10 times the amount of R115, and then we would use 10 times the amount of R22. And the nice thing about the fact that ratios are unitless is that these grams here really aren't important. So let's just circle these. Grams here, grams here. Grams don't matter. What matters is that the units are the same. So if we wanted a whole bunch of refrigerant, we could say for every 64 pounds of R115, there are 61 pounds of R22. So we can swap these out. For any other type of unit that also measures weight. So we can swap these out for other weight units. And that's kind of nice. So before we flip the page, let's check out a few rules about ratios. The first is the one that we already talked about. Ratios do not have units. The second thing is that even though they look like fractions, we never write ratios as mixed numbers. So I know you were looking at this 64 over 61, you saw that it was improper fraction and you wanted to make it into a mixed number. But if we did, what would the whole number be talking about? Right now, the 64 is talking about an amount of R115. And the 61 is talking about an amount of R22. And if we mess around with the fraction and turn it into a mixed number, we destroy the meaning of the ratio. That's the other reason why ratios are never written as whole numbers. If it turned out that the numerator was 3 times as large as the denominator, we'd write 3 in the numerator and a 1 in the denominator. Again, we have to have 2 pieces because we're comparing 2 quantities. But just like fractions before, we want to make sure to write a ratio in lowest terms. My star just doesn't seem to want to stay today. There. All right, let's flip the page and try some examples. We have a fan pulley connected to a motor pulley. The diameter of the fan pulley is 5 1/4 inches. The diameter of the motor pulley is 3 1/2 inches. We would like to find the ratio of the motor pulley's diameter to the fan pulley's diameter. So the motor pulley gets mentioned first. That acts as the A. The fan pulley gets mentioned second. That acts as the B. All right, let's see. So we need the motor in the numerator, and we want to talk about the fan in the denominator. The diameter of the motor pulley is 3 1/2 inches. The diameter of the fan pulley is 5 1/4 inches. You already know that the common units are going to cancel out, but we really don't like having fractions within fractions. So let's see if we can't clean this up a little bit. Let's take the numerator and we'll write it as an improper fraction. So 2 times 3 is 6, plus 1 more is 7. The numerator is 7/2. The denominator, 4 times 5 is 20, plus 1 more gives us 21. The denominator is 21/4. So what we're really looking at is 7/2 divided by 21/4. And working with fractions wasn't that long ago. You know how to do this. 7/2. When we divide fractions, that's the same as multiplying by the reciprocal, 4 over 21. We want to look for some common factors. Let's see, 7 goes into 7 one time, 7 goes into 21 3 times, 2 goes into 2 one time, 2 goes into 4 twice. So when we finish here, The numerator is 2, the denominator is 3. All right, so let's see what this says. What is this really telling us? The motor is like 2 units, the fan is like 3 units. So let's try this here. For every. To what? Do we have to keep inches? Absolutely not. Any unit of length will work. So let's just write that generically. For every 2 units of length, of, what was the numerator? That was the motor. Of motor pulley diameter. There are 3 units of length of fan pulley diameter. So if somebody were measuring these pulleys in centimeters, it would still be for every 2 centimeters of motor pulley, there would be 3 centimeters of fan pulley diameter. If you wanted to make a scale model of this that was a whole lot larger than the original, you could talk about for every 2 feet of motor pulley diameter, there would be 3 feet of fan pulley diameter, and it would all work out very nicely. One ratio that you'll see quite often is pitch. Pitch is a ratio specified in a very particular way. This is the ratio of rise to run. If you've had an algebra class before, you may have heard rise compared to run talked about as slope, and that's true. But with pitch, we don't talk about positive slope or negative slope. We just assume that everything is running away from the high end and towards the lower end. So we just have rise, which describes the vertical distance, and we have run that describes the horizontal distance. So let's write that down. Rise describes a vertical distance, and run describes a horizontal distance. Okay, so let's see what we have here. The minimum pitch for a drain line on an evaporator coil is 1 inch of drop for every 8 feet of horizontal line, and we want to know the pitch ratio. The fact that we've got the word drop here doesn't matter. If we went the other direction, it would be a rise. What this means is that the vertical distance is 1 inch. The horizontal distance is 8 feet. And now we have a problem because a ratio needs units that are the same. So what we're going to do is convert to the smaller unit. Not that we can't convert the other way, but if you convert things down to the smaller type of unit, it just makes your calculations a little nicer. So the first thing we want to do is change feet into inches. We have 8 feet, and we know that there are 12 inches in every 1 foot. And we'll have this type of unit conversion a little bit later, but for right now it's kind of nice to see that the feet cancel out as common units, and of course 8 times 12, which you probably knew you had to do anyway, gives us the 96 inches. So the pitch ratio, we need rise compared to run. The rise was 1 inch. The run was 96 inches. And aside from canceling out the common units, that's pretty much it. The pitch ratio is 1 to 96. So what does that mean? For every 1 inch drop, there are 96 inches of horizontal line. So you can have a really long amount of horizontal line, and that's fine, but every 96 inches you have to have a drop of 1 inch, and then we keep doing that over and over. Let's see, what other ratios may you see? Oh yes, I almost forgot about this one. The current transformer ratio. Current transformer ratio is the ratio of the incoming current to the reduced current. So here we have a current transformer that has an input current of 500 amps and reduces it to an output current of 0.8 of an amp. So we need to find that current transformer ratio. All right, let's just do it. Incoming compared to the reduced. So we have 500 amps in the numerator compared to 0.8 of an amp in the denominator. And just for emphasis, we're going to watch those common units cancel. Oh gosh, and now we have a problem because there's a decimal sitting down here, and what we really want is a ratio of one whole number to another. So if we were to multiply the denominator by 10, then 0.8 would turn into a regular 8. And of course, what you do to the denominator, we have to do to the numerator. So multiplying 500 by 10 will give us 5,000. Let's talk about common factors. Any common factors? Well, certainly 2 is a common factor. That would give us 2,500 in the numerator and 4 in the denominator. 2 is a common factor again. That would give us 1,250 in the numerator and 2 in the denominator. Everything's still even, so 2 is another common factor. And that would give us 625 in the numerator and 1 in the denominator. Now maybe you knew already that 5,000 was divisible by 8 and could have gotten to the answer faster. That's fine. Or maybe you just used your calculator and did 5,000 divided by 8, and that's okay too, but really only in this case because the answer is a whole number. If we were talking about a current transformer ratio, you would probably see it written with a colon and say it's 625 to 1. And of course what this means is that each input of, right, because the first number talks about the input. Since this is current, it's normal to talk about amps. So each input of 625 amps is reduced to 1 amp. And that's one thing that the current transformer ratio will tell you. The other thing it tells you, since the denominator is 1, is that the incoming current is 625 times larger than the reduced current. And that's pretty useful information. And that's the only type of information we would get because we're comparing our quantities using division. Okay, so let's shift gears from a ratio to a rate. Rates are almost exactly the same as ratios. A rate also uses division to compare quantities. The thing about a rate is that we have different units. And since the units are different, they don't divide out. So when we get done, we have to talk about numerator units compared to denominator units, which means that we also often see this written with the word per. And we've done this before. Division gives us a lot of things that involve per. Let's try an example. We have a 9-foot section of duct that weighs 12 pounds. We'd like to represent this information two different ways because they ask us about which two rates. So the way we can do this is we can start off by comparing feet to pounds. So if we say 9 feet for every 12 pounds, we can certainly write that fraction in lowest terms. Both of these have a common denominator of 3, but the units are still there. 3 feet for every 4 pounds. So we can say that 3 feet of duct weighs 4 pounds. If we kept on going, we would get what's called a unit rate, and we'll talk about that in a little bit. 3 divided by 4 is 0.75. Now let's just write it down anyway. Why not? Divide the 3 by the 4, we get 0.75, and the question is 0.75 what? Numerator units are feet, per represents the division, and denominator units are pounds. Oops, sorry, feet per pound. That's better. So 3/4 of a foot of duct weighs 1 pound. 3 feet of duct weighs 4 pounds. All the same type of information from that beginning comparison. Well, they asked us for 2 rates, so let's go the other direction. Let's compare pounds to feet. If we have 12 pounds for every 9 feet, writing the fraction in lowest terms, this is just the reciprocal of what we had before. We still have a common factor of 3, so we have 4 pounds for every 3 feet of duct. 4 pounds of duct happens to be 3 feet long. These two here, this sentence and this sentence, are saying exactly the same thing. But if we did the division, 4 divided by 3 is 1.3 repeating, 1.33333, because you know that a third is 0.3 repeating. So we're just going to round this to the nearest tenth. We'd have 1.3, and what would our units be? Pounds for the numerator, per, and feet for the denominator. So that each foot of duct weighs 1.3, sorry, about my little approximately in there, pounds. And that's slightly different than what we had before. 1 pound of duct is 3/4 of a foot long, but 1 foot of duct weighs 1.3 pounds. But that's pretty much all there is to rates. So let's see if we can't put these ideas here together and talk about those denominators. If we keep on going with the division until the denominator is 1 and we end up with a decimal or something like that, we end up with either a unit ratio or a unit rate. A unit ratio is a ratio whose denominator is 1. And we had something like that a second ago. Whoops, sorry about that. We had something like that a second ago when we were talking about the current transformer ratio, right? We had a ratio of 625 to 1. A unit rate is a rate whose denominator is 1. And we just finished that. Let me come back up here so you can see. All right. This one is a unit rate. This 0.75 feet per pound is like this, 0.75 feet for every 1 pound. This one, whoops, yeah, this one is also a unit rate. 1.3 pounds for every 1 foot. Okay, and as we saw, if you force the denominator to equal 1 and actually do the division, you of course end up with decimals and fractions. A compression ratio is the ratio of the discharge pressure to the suction pressure, but both of these have to be measured in absolute terms. So let's write that down. Compression ratio is the ratio of the absolute discharge pressure as compared to the absolute suction pressure. This is one ratio that you will see almost always written with a colon. And we have to remember that these are in absolute terms, so maybe we'll highlight this, absolute, in both places. Here's how it works. We want to compare discharge to suction, because that's the way the ratio is always written. We need absolute pressures. So let's see, the discharge pressure of a compressor is 127 psig. So to turn that into psia, you know that we have to add the 14.7, so we are including atmospheric pressure. We'll do the same thing down below. 10 psig turns into psia by adding that 14.7. Let's see, the numerator, 127 plus 14.7 is 147 psia. And in the denominator, that's 24.7 psia. And even though we know that the units are going to cancel out, it's not a bad idea to write them down the first time just so that we don't forget to actually convert to absolute pressures. Otherwise, we're just going to divide. 147 divided by 24.7. And the calculator says we get this thing, which we're going to round and say this is about, whoops, oh my gosh, I can't add. Hang on a second, what did I do? 127 plus 14.7 is not 147. You should have said something. Yeah, I know, just kidding. It's 141.7. That's better. Let's try that division again. 141.7 divided by 24.7. It still doesn't come out to be a clean answer, but I recognize this one. Let's round the answer to the nearest hundredth. So we'll say that this is about 5.74. But not just 5.74. Remember, this is a ratio. We have to compare two things, so we need two numbers. This is 5.74 compared to 1. So the compression ratio is 5.74 colon 1. And of course what this means is that the absolute discharge pressure is 5.74 times greater, or times larger, or times as large as the absolute suction pressure. And that's pretty much all there is to it. Let's try one here. We have a solar panel with a surface area of 6 square feet. It produces 75 watts of electricity. Your job is to calculate a unit rate, which means we want to carry out the division all the way, comparing watts to square feet. All right, you should pause the recording, take a second, try this one on your own, and then come back. And hopefully your answer starts off like this. Watts is in the numerator because it's mentioned first, compared to square feet in the denominator. 75 divided by 6 is 12.5. But the question is 12.5 what? So 12.5 watts from the numerator per square foot from the denominator. So every square foot of solar panel produces its own 12.5 watts. Go the other way. Pause the recording, compare square feet to watts with a unit rate. You start off with the reciprocal of what you had before. Because we are comparing square feet to watts, the 6 square feet goes in the numerator, the 75 watts goes in the denominator. The division gives us 0.08. The question is, what are the units? 0.08, hopefully you wrote down square feet, because that's what was in the numerator, per watt. So if you only wanted to produce 1 watt of electricity, you would just need 0.08 square feet of solar panel. And that's pretty much how it works. One more thing to do, and then we'll call it good for today, and you can all get started on your homework. So the last type of unit ratio or unit rate that we want to talk about specifically targets price. Unit price is the price for 1 unit of the item. Since the denominator is 1, that makes it a type of rate. So this is price per unit. And it's always done this way so that the dollars will be in the numerator and the number of units will be in the denominator. So regardless of what the economic realities are of whether or not we can afford to buy in bulk or things like that, the better buy is generally determined by comparing unit prices. We're looking for the lowest unit price when we talk about the better buy. So let's see, envelopes. Every business needs envelopes. We have a box of 500 envelopes for $28.69. Let's find the unit price for that as compared to the box of 125 envelopes that's on sale for $5.99. Let's see here. What do we have? We have a small box, and we'll compare it to a large box. For the small box, right, we went dollars per unit. So this is $5.99 for every 125, and these, of course, are envelopes. Calculator will help us with the division. 599 divided by 125. Leave all of the decimal places there. 0.04792, because we don't know how many of them we're going to need for this comparison. But the units here are dollars, because that was what was in the numerator, per, and the denominator talked about envelopes. Oops, per envelope. There we go. So it's just about 5 cents an envelope. Pause the recording. You give me the unit price for the large box, and then come back. And hopefully you came up with the same thing that I did, starting with the $28.69 in the numerator, dividing by 500 envelopes in the denominator, and this comes out to be $0.05738 per envelope. So if you needed a bunch of envelopes, this is the week when you should buy several small boxes instead of a few big boxes. And we will label this sale the better buy, because it has the lower unit price. All right, and that's it. Good luck with your homework, and we'll see you in a little while. Take care. Bye-bye.